So I think maybe we could start. And as you said, maybe Hugo and Diane can present themselves because it's the first time they are attending to this kind of meeting. So maybe you can talk a little bit about you and what you are doing at ESA, and then we can proceed after that.
You mean me? Yes. Hello, I'm Diane. I'm a new young graduate trainee. I'm here to join the software team, specifically on this project, because for my master's degree, I mostly studied how AI can detect and influence conflict. So I use a lot of sentiment analysis as well. So they figured I'd be a good fit for this project. So it's nice to meet all of you.
Nice to meet you.
Nice to meet you.
Okay, so now would be me, I guess. Good morning, my name is Hugo. I'm a Portuguese national trainee with a software technology section. I just started in the beginning of September, so more or less 2 months now. I'm working with Luis mainly with artificial intelligence for space applications. And yeah, and I've been following a little bit about of this sentiment analysis work from other two my colleagues, and I'm interested in knowing a little bit more.
Nice.
Thank you. Nice to meet you.
Yeah, nice to meet you. Thank you.
And I think Alex just connected, or not?
Yeah.
Oh, no. Oh, yeah. Hi,
hear me?
Alex. Yes, we can hear you.
Yeah, I'm sorry for the delay. Troubles with the Microsoft Teams. Yeah, anyway, I'm Alexander Zöchbauer. I'm an intern here in the SWT section, and I've been working here since February. And on the sentiment analysis, started with Luis like a couple of weeks ago. And yeah, I'm eager to hear what is getting presented.
Yeah.
Nice to meet you, Alex.
Nice to meet you.
Nice. Yeah. Thank you for joining. Yeah, thank you.
I think that's all from our side at
Great.
this moment. So
then we can start.
Whenever you want. Yeah, please.
Yeah. Welcome, everyone. Welcome to the midterm presentation for our project. The project is called Sentiment Analysis for Astronauts. This is still a title work in progress, and it will most likely change to another title next week because we want to call our system a certain way. Let me first go over the topics of today. First, I want to do an introduction of the PDEng. Who are we and what do we actually do? I want to go over the problem statement and the solution proposed. Then go over a global architecture, give a global view over what we're doing. Then go more in depth about the video architecture and the progress. Then about the audio architecture and the progress. Eventually, we go into the integration of these two. And then we want to show the current results that we have gotten so far. So who are we? We are the PDEng software technology. And to explain what a PDEng is, because not for everyone it's well known, let me first do the regular go through in academia. So first you would do a Bachelor of Science, as we all know, which takes 3 years in the Netherlands. Then you would do a Master of Science, which takes 2 years. And after the Master of Science, you have a couple of choices. You can either go into industry and join some companies, or go further into academia. And even in academia, you have multiple choices. The most well-known choice is doing a PhD, which is a Doctor of Philosophy, where you go more into research of a certain specific topic, and it takes 4 years. However, on the same level, you can also do a PDEng, which is what we are doing, which is a professional doctorate in engineering. And this takes 2 years, and it's what we are in right now. And to compare the PDEng to the PhD, we have this graph. On the bottom part, you can see the PhD, which is more to the fundamental side. It's really research-based on a specific topic. You go really into depth in that topic, and it's more about fundamental science. And the PDEng is more pragmatic and also a bit more application-oriented. What that means in practice is that we work together with large companies on real problems and real solutions. And often that means we're doing projects such as this one for multiple companies. So that's who we are. So now that we know the PDEng, let's show our faces. In the top left, you see me. I'm Juan. I'm the project manager for this project. Then we have Tom and Gilbert, which are the two team leaders for our project. We have Chris as our lead architect. We have Louise and Yusriel as our software architects. Niels as our Scrum Master. Nathan as our engineer and supporting Scrum Master. Jorge as our configuration manager. Samson as our engineer and configuration manager. George as our test manager. Han as our quality manager. And then Raha, Vladimir, Parima, Tuvi, Akram, and Hossein as our engineers. So as you can see, we have quite a large and diverse team. And that's what we're working on, with whom we're working on this project. So let's introduce the project a bit more. And for that, let's first state the problem that we're facing. As we know that in space missions, it can often be stressful and a lot of emotions can happen for an astronaut. And what is really important for an astronaut to keep a healthy emotion and preserving this healthy emotion. However, this often is quite hard because of all the external factors. So what we want to do is we want to assess the emotional state of an astronaut. Also, this is quite difficult since often we're dealing with a far distance, which means that we often don't have a connection with the astronaut. We can't ask him how he feels. So we have a really hard time assessing how the astronaut actually feels. So taking these two problems in mind, ESA came up with a solution for this, which is develop a system for facial and speech sentiment analysis. What this practically means, you can see on top, you see an astronaut, and we have a video and an audio stream, and we detect what the current emotion of an astronaut is. And in this system, we use artificial intelligence. Well, this is a really basic global view of what the project is about. And I want to go a bit into the project structure. So for this project, we use the ESA standard in terms of phasing, which means that in the first 3 weeks, we have the user requirements phase, where we define all the user requirements for the system. Then from week 4 to week 6, we have the software requirements and architectural design phase. Then in week 7 and 8, we have the design and production phase. And in the last 2 weeks, we have the transfer of the software phase. And right now we are in the midterm presentation. So we're sharing our results and we are in the middle of week 5. So we have wrapped up the user requirements phase. And right now we are in the software requirements and architectural design phase. Well, as also proposed by ESA, these phases often come with lots of documents, of which the user requirement document is now sent, and the software requirements document and the architectural design document are work in progress. And what we're still going to do in the last weeks are the detailed design and production document, the software user manual, and the software transfer document. So coming back to our system, developing a facial and speech sentiment analysis system, I want to give the word to Chris, which will give you a global overview of the architecture that we're using.
Yeah, thank you, Juan. So good morning, everyone. As Juan mentioned, we need to have a system that will combine using artificial intelligence with an application that is based on video and audio, because this is a good way to try to identify emotions from facial features and basically the tone of voice that you're using, the pitch. And these things combined, there are applications in artificial intelligence that allow us to do this. So on the one hand, we have an application and we need to have an overall design. The high goal that we have is that we want to actually develop an architecture and a pipeline that's flexible, extensible, and customizable. The idea here is that certain technologies might change over time. For the project, we're actually using Raspberry Pi single board computers, and this is probably not qualified for space use. ESA has their own internal system on a chip and different type of microcontroller units that they would use for these missions. And the idea is we want to be able to switch these out. Furthermore, AI is a rapidly developing field, so the models and the machine learning models and the AI models that we create or that we use these can change over time, and you want them to be able to change. So the idea is that we should be able to define the interfaces, the model structures, and the way that the data formats, how things are communicated through a pipeline to be able to be adjustable in the future. The specific application that we're going to be using is based on video and audio, because this system will be able to analyze and predict and classify the different facial features. So if I'm smiling, I'm probably happy. If I have a nice tone in my voice, I might be happy. And conversely, if you have negative tones and negative facial features, you can detect these with audio and visual sensors, particularly cameras and microphones. So now that we know that we're going to have, we can use microphones for audio and cameras for video, we can view our total system in basically 2 different channels. On the top you see, on the top you see we have an audio channel, and on the bottom you see we have a video channel. So we've actually broken this into different layers, where we have a user layer, which is the astronaut, an input layer for the sensors, an AI layer, which is actually where the modeling and the processing takes place, some output, and then later on we'll have a fusion layer. So for the audio layer, of course, if the astronaut is talking, right, like a microphone can detect this speech, and it can break it into its frequency components, so the tones or the pitches, as well as the actual things that the astronaut says. So these are the utterance-based or text-based words, right? The actual words in the sentence. Because what you say and how you say it, they can provide a lot of information into how you feel at any given time. The idea is that we will get an output of a happy tone if the speech is happy, and we'll be able to identify words that are associated with happiness. On the video channel, we have a little bit of a different process. The camera is streaming the application, so it's actually monitoring the astronaut in real time. It's going to actually try to do some detection of the facial features. So this bounding box over the astronaut's face is trying to show that it's detecting the smile. And then it's going to extract that there's a happy expression of the astronaut. So this can be done a number of ways. And the idea is that you'll be able to actually classify that based on their facial features at a given time. They're happy. Then the idea in the end is that we take these 3 results and we combine them. So we either do some type of fusion or some just combinational statistics, so we can get a better confidence in our prediction. Now I'm about to hand it over to the video team, which is Yusril. He's going to give a nice presentation on the video, and then after which Luis will follow with the audio. Thank you.
Thank you, Chris. So I'm going to explain more about the video part of the system. Yeah. So this is the overview of the video architecture. We have 2 parts here. The first part is the training part, and then the second part is the prediction part. Now I'm going to explain more about the training part first. Yeah, in terms of data set, we are using that RAFDES data set. And in this data set, we use specifically the video part. And for each video, it has an emotion level. For example, like calm, happy, and so on. From this video, we try to extract the feature by using two steps. First, we convert the video into sequence of images, and from that sequence of images, we detect the face because in order to get the facial expression, that's the most important part of the image. And then after that, we train the model, our model. And then worth to mention also that we use an optimizer which is OpenVINO, so that we can get a better performance. One of the reasons because we use Raspberry Pi as our hardware, so we have to take into account about the performance as well. And then finally we get our trained model. Now I'm going to explain about the prediction part. Yeah, it is worth to mention that we use Raspberry Pi as our hardware, and then the compute engine stick is also provided. So that's why, because we have a limited research, we have to really think about the performance of our model. And then first, as in the architecture of the prediction itself, first we have the input. It can be a live streaming or a recorded video. And again, we try to extract the feature by converting the video into sequence of images. And then we detect the face. And since we already have the model from the training part, we can simply let it predict the emotion, and then finally we get the predicted emotion. So go back to the overview of the video architecture again. So far, this is what we have done in the last 5 weeks. So what can possibly be done in the next 5 weeks? The first possible improvement is the feature extraction part. Here, there is something that is still under investigation. It is called subtraction preprocessing. And also, in order to get the subtraction preprocessing, we also need to do the face alignment. But again, especially the face alignment part, it's quite demanding in terms of the performance. That's why it's still under investigation, since we are going to use the Raspberry Pi, so we have to be very careful on that. And the second possible improvement that we can do in the next 5 weeks is this part, the model itself. So first we can try another architecture neural network, and also we can also play around with the hyperparameter tuning in order to increase the accuracy. Now we are going to have a demo, and now I will hand it over to Hussein and Vladimir.
Thank you, Yusril. I'm Hussein, and with our astronaut Vladimir, we're going to show you a short demo of our video part. I ask Vladimir to run the script. The demo that you are seeing is running on the Raspberry Pi. As Yusril already explained, the camera module and neural compute stick are also installed on Raspberry Pi. The camera captures the frames, then face will be extracted from the frame and will be sent to optimized model to detect the emotion on Raspberry Pi. As you see, predicted emotions are also shown on the screen and can change based on the mood of astronaut. After this, we should focus on the performance of model. And I think that's the demo that we have for now. I give the words to audio architect Luis.
Thank you, Hussein. So here you can see the global architecture again. Now we are going to focus in the audio part. As Chris mentioned already, the audio part is divided into tone and text. So let's deep into this. This is the general overview of the audio architecture. On the top part, we can see the training part, and in the bottom part, we can see the prediction. The general architecture is very similar to the video architecture, but the only difference is that we are going to use audio. Let's deep into the training part. So for the tone model, we are going to, we trained it with the RAFDEX dataset, just like the video team did, but in the RAFDEX dataset, you can find samples of audio and video, and we are going to use both of them instead of only video. These samples are recorded from multiple actors, and they come labeled with some emotions, so we can use them for training the neural network. Before processing the audio signals, we have to convert them into MFCCs. These are the features that we can use for training the model. The MFCCs are the male frequency septal coefficients, and they are obtained by doing a series of transformations into the audio signal. Basically, these coefficients are a way of assigning a number to a phoneme. And these numbers are the ones that we can feed into the neural network to actually train it. This is the way we obtain the model based on the tone. For the text, we cannot use the roughness dataset because it only has 2 different sentences, so it's not useful for training based on text. So we use these 3 datasets: the MEL, the ICR, and the TWIT. On these datasets, we also have examples of different sentences, and we assign an emotion to each of them. In a similar manner, we have to extract the picture. So what we do here is what is called text vectorization. Basically, for each word, we assign a number, and these numbers are the ones that we use to train the model. After we have trained the model, we obtain a model that is able to classify emotions based on text. And if we go back to the overview, once we have trained the model, we deploy them in the Raspberry Pi. And let's deep into the prediction. So all this prediction takes place inside of the Raspberry Pi. Here we have, as an input, we can have a live stream or a previously recorded audio. And in a similar way of training, we have to extract the features. That means the MFCCs or doing the text vectorization. One extra step that we have here is that from audio input, we have to convert this audio into text, and we have a small module that does this. We have the 2 previously trained models, and with those, we obtain the emotions. So this is the current progress of what we have, and right now we are starting a phase of trying to improve the results. So, for example, for the feature extraction, we want to experiment about removing the silence on the audios. So we will remove the silence at the beginning and the end of the audio. And we also want to try to do some techniques of framing. So we can separate the audios in more specific features, so the training is much better. Another thing that we want to try is, right now we are using CNNs for both models, and we would like to explore the possibility of using RNNs. So in addition to the value that the information that we have in the data, we also want, in the current data, we also want to extract information from the previously trained data. And after this, I'm going to handle the presentation to my colleague Jorge. He's going to show the audio demo.
Thank you, Luis. Let me share my window, which this one. And I hope you can all see it. So what we are about to see is the result of the last weeks. We are going to show how the sentiment analysis for audio models work. And the process in general works as follows. we are going to see a program that says 4 things. First, record for 5 seconds, and then we have to say something. Then the analysis will start, and we will see what the recognized text is for the text-based sentiment analysis model. Then we will see the predictions of both models, the audio-based and the text-based, and then we will have a pause before repeating this process again. Short disclaimer here, these models were trained with data that has different accents from the ones that we are going to present now. So expect unexpected results. That is possible. And I want to show you, if you can still see in my camera, this is the Raspberry Pi that we are using with the microphone that was provided to us. And I'm going to start the program. Right now, it is loading the libraries that it requires. So it's going to take a couple of seconds before it can show that it is ready to start working. And now I have to speak for 5 seconds. I feel so tired. Let's see what it got. Oh, interesting. I'm very calm. And the text prediction says, I am disgusted. And to show you that this is not a trick, that it was not pre-recorded, I'm going to set up my speaker. I'm going to take out my earphones. And now I would like to ask Juan if you can speak for the next time.
I can. I'm very happy with how good this demo is going.
Cool. Well, we got some calmness and neutrality. And now, Luis from ESA, if you would like us to speak the next time.
Sure, I can try. So now?
Yeah, I didn't already record, but we can wait for another round. When it says speak for the next 5 seconds, you can do it.
Hello, everyone. I'm really happy to be here today. I'm quite thrilled about the... Oh. No, I'm not disgusted.
Yeah, we know. These are the unexpected results due to the accents that are available in the dataset. We are working on this.
We need to train with the Spanish-English accent, the model.
Indeed. And now I give back the presentation to our partners.
Chris, can you take over?
Yes.
Nice.
Okay, there we go. All right, I'm back. Nice to see you again. So as you recall, we have this global architecture, and now you've actually seen the presentation results from recently the audio team, and previously we saw it from the video team. And if you look at the architecture, you'll see that there's some similarities here, right? And those similarities are in actually the way the project or the pipeline is structured. So the next thing I would like to talk about is we call it integration, but it's actually the architecture pipeline. So here's our general architecture pipeline. We know that we have data sets which can have different types of data. So this can be visual data, text-based data, or the tone-based data. We have 3 major modules that we're using. One of them is called a data wrangling module, where we do a lot of our pre-processing. Another module that we've called is the model. So this is actually where most of the AI happens. And then we have a deployment module. So this is actually when we want to ship and build our basically our model on some hardware. In our case, for this project, we're using a Raspberry Pi. And we actually do the real-time analysis in the real-time runtime environment here. And then we will log the results. This is the idea. So let's look more at the data wrangling module. The different data sets, they exist, and we can even create more. Basically, you want to take in this data and do some labeling. So this is actually just looking at the category of the type of data and make sure that it's well specified. You'll have this actual pre-processing step. So this might include data cleaning, which is like the removal of noise, or for the audio, trying to cut off some of the time. In the beginning, there's some silence, and at the end, there's some silence. Data integration here is actually if you want to consider using multiple sources or multiple data sets at the same time. Data transformation has to do with things like normalization or different things that you need to do to your data to get it all structured a certain way. And data reduction here is actually trying to remove things that are not necessary. So if we want to develop our system to mostly focus on negative emotions, for example, like anger, then if we have some type of emotions that are less relevant, we can reduce the data here if we have issues with that. Or if there's some data sets that have different emotions in them and they don't line up, you can remove it here. After this pre-processing step has been completed, we will split the data. So the data becomes split into your test, your training, and your validation sets, which goes on into our model module. So then we have a split here. The way we're differentiating now is we have our training set and we have our test and validation sets. I've just combined them together because that's usually how they're represented in AI. Down here, you'll have your model engineering. So this is kind of your feature engineering, your hyperparameter tuning. So you do things to make the model better. Then you have some model evaluation. This is where we actually apply our metrics. So if we're looking at the accuracy or the F1 score, we want to actually know how well is our model performing. And of course, this can be fed back into the model engineering so that way we can continue to improve. And then we test it or we validate our set, our model to make sure that everything looks the way we want. Then we have, for our architecture pipeline, we have this packaging step. So because we're using OpenVINO expects IR formats for their models. It expects this for two things. One, for the model optimization. If you want to optimize it using OpenVINO, you need to use certain layers or certain type of architectures. And then this will actually, you can optimize your model and send it back to an IR format. And then once this is all built, so let's say you did all of this on your computer, you have your model exactly the way you want, you're happy about it, it's time to actually ship it to the hardware. And we call this the deployment module. So here you will ship it to your hardware. So you need to build it. This includes compiling, do some different integration tests, make sure basically in your terminal, all of your models can run simultaneously. And then you will execute your models. After your model is executed and it's online, you can do your sensor input stage. Basically, for our case, we have this Raspberry Pi, and it has different sensors. Of course, the camera and the microphone are the most notable. And then you will go back. You will take this model with the sensory input and do some initial data processing. So this is kind of like the data wrangling module earlier, but now it's actually for the real-time or raw data. So you have to process it a certain way. Your models are executing and running and doing their detections. You'll get some output, which we want to fuse together. We call data fusion. You can also consider this data combining. It really depends on the implementation method. It's nice to visualize the results as you've seen in the demo. If the models are doing stuff and you have no way of telling, well, it's really hard to make any type of analysis or judgment on whether they're working or not, or where they need to be improved. Then, of course, we want to monitor the behavior of this over time and log the information. Logging the information makes it useful for doing things like a time series analysis or just try to drive insights or make predictions on the future. So one thing that you may have noticed is in this pipeline that we're proposing, and I'll actually stay on this slide for a moment, a lot of things are really kind of high level, right? We're trying to create a process that is easily changeable without needing to change any of these different inputs. So for example, if you have different sensors, let's pretend like later in the future you want to include a different type of sensor that's measuring some other environmental aspect. Well, the method and the interface should be the same. Or even if you have a different type of data that comes in, right now we're looking, so another type of data for visual data or for video is gesture recognition, right? We can do gestures, but we don't need to change anything in the pipeline or the architecture all the way from the start, from the end to end, to be able to get the model to run, as long as we uphold the same interfaces. And so if we have the same interfaces between these modules and we try to keep the data type the same, as long as we adhere to all of that, you can actually change out anything in the models. You could remove some of the data wrangling steps you don't need. Say you don't need to do data reduction. You don't need to do that. OK. And you can actually have a different type of hardware here. So this could be basically an ESA development platform, something like this. And then in the deployment, you could have different sensors. But the high-level architecture, you don't need to change it. So this is something we're trying to provide for ESA. And what are our current results? Well, I think you saw during the demonstration, we have some mixed results. It's probably to be expected. But right now, we have 3 different types of models we're running. So for the video, we're using for a convolutional neural network. We're using it with MobileNet, and the current accuracy is about 53% or so. And in the future, we want to use some different network architectures. We need to do some more hyperparameter tuning, and then we have this preprocessing step called subtraction, where it kind of looks at the distance between some of the neighbors. We want to look at these in the basically next upcoming weeks. For audio, we're currently using more convolutional neural networks. The frequency component part is actually relatively high accuracy at the moment. Again, it depends on the accent, but we'd like to add recurrent neural networks if possible. We're maybe limited on the hardware. Of course, do more hyperparameter tuning and look at the preprocessing and the data steps to improve that we have, improve the data that we have. For the text-based model, we're still using convolutional neural networks for this as well, but they generally work better with, they have the potential to work better with recurrent neural networks, but there's some limitations based with OpenVINO and the hardware we have right now. As such, our accuracy is a little bit low. Earlier it detected that even though Luis said he was happy, it thought he was disgusted. So as you can see, these are definitely things that we have, we're working in progress. Right now, it's about getting everything set up, everything working on the Raspberry Pi, because this integration step can be quite, it's not trivial at all. And now we actually, based on the way we've designed the system, we can change out the models anytime we want. So if we get a new model that performs better than, well, for right now, just convolutional neural networks, but if we get a different model that outperforms another one, or we train with a different data set, it's really easy to just plug and play these different modules. Also in the future, we need to do our actual fusion. This is going to use multiple models because whatever these models are up here, it's going to be combining the results of them. There's also a different, 2 different approaches for this. There's basically a statistical way of doing this where we actually take the previous accuracies and we try to do some weighted distribution. So there's always this option. A more interesting option is using another type of architecture called transformers. They're really fun, but we might not have the hardware necessary to be able to run these, because you have to ask where are you going to put it? How's it going to run on the Pi? Which Pi should it run on? So these are things that we're kind of we're working on right now. Here, accuracy will be a little bit of a different topic because we're actually looking at the confidence level and combining these confidences to actually give some indication whether or not what the previous models have classified, is that really the emotion that the astronaut has, and how confident are we that this is correct. So the idea is that if we combine these 3 models together, the results of these models, we should get a relatively good prediction depending on the confidence level we get. And that's the work in progress for that. And at this time, we would like to ask you if you have any questions, and we want to thank you for your attention. We hope that you had fun, and please let us know if you also have any suggestions. We're open for them. Thank you.
Thanks for the presentation. From my side, I have a couple of questions myself. Maybe I can ask now. But I want to say that I'm really happy to see the progress, and I can see almost all the different building blocks are already in place. So it's just a matter now in the next weeks, I would say, of training more the models to get a better accuracy and deploy optimizing. But at least the whole view of the application is quite clear now. So that was quite useful. I have, for example, I saw you are using mobile net right now for the and I guess you said that you are considering to try to use another other kind of architecture. I don't know, ResNet, or is in your roadmap?
Yeah.
Nice.
Yeah. I guess that's a question for video architecture. Yeah, we tried AlexNet in Inception, V3, MobileNet, and ResNet, and we compared them. And so far the highest accuracy is the MobileNet. And I think you also indicated that as your first guess. And also we also consider about the prediction time. And since MobileNet has the simplest one than the other one, so here based on our investigation, it has a faster prediction time. So that's why for now we use this. But again, we will do some more investigation with another type of INN.
And but now that you're talking about the prediction time, how much longer are you waiting till run one inference? How many seconds are you waiting? Or is every second, or is every 2 seconds, or?
Oh, for now, I think I'm not sure about that, but I think for Hussein and Vladimir, you can answer it better.
Hussein or Vladimir? Can
you repeat the question again? Was it about the time
prediction? Yeah, the time of the inference.
Yeah.
Yeah, I don't have an exact time, but it's like 5 millisecond, or you mean the detection time or the
the prediction time?
I mean the inference, yeah.
Yeah. So the prediction time is 5 milliseconds.
Okay. I don't know. It's a suggestion. Maybe it's like we don't need to run an inference every 5 milliseconds, because maybe there is no much information in between 5 milliseconds and the next 5 milliseconds in the phase. So maybe we could even wait longer. Maybe we can wait like 2, 3, or even 5 seconds till run an inference and see if the phase has actually changed. I think this is also quite related with the subtraction preprocessing approach that I hope you have time and you are able to implement it, because I think it's quite interesting, and it will bring this time perspective more into the model. Yeah. Because maybe every 5 milliseconds is too quick. And I could see also during the presentation that the inference was changing really quick, so it was difficult to follow. Maybe something we can do is like if we establish, it's a suggestion. At the end, it's of course it depends on your own experiments, but maybe we can put something like, if it's, let's say we establish 5 seconds, for example, then we can put something like acquiring data in the interface, so the user knows that at that moment we are not running any inference, and then once we have if you are using I don't know 1 frame per second, then once we have 5 frames for those 5 seconds. You run the inference, and then you can see clearly which is the output for that inference. This is a suggestion to make clear exactly what is going on. Yeah. But again, I think this is quite related to with the subtraction preprocessing. So I'm looking forward to see what you can come up applying that.
Yeah. About the subtraction. Oh, yeah. Please go.
So we have seen in the benchmarks that the actual inference is quite quick. So that's where the 5 milliseconds come from. Currently, we don't infer every 5 milliseconds.
Okay.
So there is a delay. It's currently measured in repetitions of a loop, not in seconds yet. But what we see is that the current bottleneck is actually the rendering of the video stream on the Pi. So we see clear performance difference between running the system on a laptop and on the Raspberry Pi. But the actual inference is quite fast, but the actual drawing of the frames in the little window, that's actually the bottleneck, because the Pi doesn't have a GPU, and that's why it is lagging a little bit. So I think we can have quite good performance, but we only have to see how we render the output. So that's the current state, basically. And I do agree with you that we should look at a useful interval where we render outputs. So that needs to be tweaked.
Okay, good. Thanks for the clarification. So yeah, you're already then aware of this. Awesome. I was going to say something regarding the audio team. I remember from previous meetings that you were considering using different data sets, extra data sets. I don't know, did you have time to apply those data sets in the training, or is just something that you're gonna do later on?
Well, the only difference from the last time we talked is that we also added the audio from the videos in the roughness dataset, and that's one of the things that we also want to increase, because the more data you have, the better the results. But for now, we are only using roughness.
Okay.
But in the following weeks, we will study the possibility.
Okay, because I remember you already did quite a nice analysis on a viable free data set. So I think it could be quite interesting if you have time to apply those. I think it will improve a lot the model, as you say, and you all know. So, and for the audio models, are you considering also optimization? I don't see that in your.
Well, we already started doing some optimizations. This past week, we worked a lot into improving the accuracy of the tone-based classifier. The text-based classifier still doesn't have that good of accuracy. We are still exploring the possibilities of using another neural networks that could give us better results. But then again, we will want to focus. We also want to do some optimization. Right now, I think the classification and the prediction is quite fast. So we will see what is needed to do.
Okay, so, nice, sounds good. Just want to mention that maybe in this case, because you mentioned that you would like to use a recurrent neural network, for example, and there is this. We are aware of this incompatibility issue with Myriad and OpenVINO for. It's more with Myriad than with OpenVINO for recurrent networks. But I wanted to say that in that case, maybe you can run actually the model in the Raspberry Pi. You don't need to deploy that in the in the Myriad chip. The decision at the end is up to you guys, but it's something you might want to consider. And if that's the case, you might want to use you might want to use, for example, TensorFlow Lite for optimization. So the same way you are using OpenVINO to optimize the video model when you are deploying the model into the Myriad. In this case, instead of OpenVINO, you can use maybe TensorFlow Lite. It's again a suggestion. At the end, it will be a trade-off that you need to let's say to find between especially when it comes the moment when you might want to put all the models together in one Raspberry Pi. That's going to be quite challenging at the end. So yeah. you might need to consider maybe at that step is needed an optimization or not. But I just wanted to say that don't, let's say, don't give up on using recurrent networks or even transformers, as you said, just because it's not compatible with OpenVINO and with Myriad, because maybe you can just run the inference in the Raspberry Pi. And also, I noticed, but I think it's because of you still need to train a little bit more the models. I noticed it's a little bit biased toward negative emotions, because in both cases, I saw in the case of the video, I think it classified angry when your colleagues were clearly smiling, and in my case, for example, also it was upset. That's related with the fact that still more training needs to be done, or is related because we also had this conversation of actually intentionally bias a little bit the models towards more negative emotions. It's not that the case, right? It's just that it still needs more training.
No, I think it's a bit biased to the angry tones because the data set we saw the recordings and the people talking in the angry tones, they have a stronger I don't know, emotion. So I guess that is the thing that is biasing the models a bit. But I think we have quite good accuracy in the tone base. Work in the tech base that is more difficult.
Okay. Then from my side, I don't have more questions. I just want to thank everyone for the hard work so far. I'm quite happy to see the progress so far. I think we are on the right track, and the next week are gonna be quite fun for everyone, and is when we can actually tune more everything and get better results. But as I said, I can see all the building blocks are already in place, and I think you guys you've already identified which are the possible future risks, especially in terms of restrictions with the hardware that might limit the models that you want to use, especially when you want to put eventually everything just running in one Raspberry Pi plus the Myriad. So it's good that you already are aware of that. I don't know if any of my colleagues have any other question, but from my side, this moment I'm happy and no more question.
Hello, this is Diane. I have a quick question. Just out of curiosity, how do you guys do the audio pre-processing to remove silences and things like that? You mentioned that you try to compact the data a bit. What do you use, or what techniques do you use for that?
We are using a library called Librosa, and then another one that we also studied, if you want to have a look, is Pi Audio Analysis. These are things that we are still under development, but we have researched a bit about them.
Thank you.
I have also a question related to what Diana has asked, also a kind of follow-up question. And of course, in this space, the sound would be much more, how to say, distorted because of the helmet and all these things. So have you also tried to imitate that and by creating similar environment, or have you received data from ESA with such data, let's say with such, how to say, extra emotions or extra distortions?
Actually, if you want, Luis, I can cover this one. Even though our design has like the astronaut has the helmet on, in general, we're not looking at whenever they go on EVAs, extravehicular activities. We're actually mostly looking at them when they're inside either a deep space module or the International Space Station. So actually, we forgot to make the disclaimer that the astronauts are not actually wearing their helmets at the time. This would be a more challenging process. You would need to integrate basically with the onboard computer of the spacesuit. If they were wearing it, it would actually need to be integrated into the helmet, and there would be distortions and feedback cancellations like this.
All right. Okay. So I think that also cancels my another question. So actually, the scope is without the helmet, and indeed it's inside the ISS. So right. Okay. That's clear.
Yes.
Another one was on the validation side. So I saw on your slide there is some validation, but do you how are you validating both audio and video samples, and with, for example, Vladimir gives very explicit, in this case very explicit emotions, but there are sometimes people who don't show that emotions, especially Russians, let's say. They all look very grumpy, but they might be happy, right? So have you considered that kind of validation?
Yes. This is actually a really hard topic for us because, like you said, different type of people express emotions differently. One suggestion that we have is that if it would be possible to have astronauts create their own individual training data set, so that way during the 3 to 4 years they're training to be an astronaut at ESA, if you could document this is when you have the highs and lows of your life, is when you're doing your training. The idea is if you could actually make individual data sets, you could really easily validate this. In terms of now, it's a little bit challenging, and we're still working on this validation and the verification process because we're taking basically data from actors who are very expressive, and we're applying it to people who might be cosmonauts, Russian people that might not, I am smiling, but from our perspective, it doesn't look like smiling. So we do know that this is a key issue. We've been in discussion for it. We're trying to resolve it.
Right. Okay, so that can become also kind of future work. Okay, another one was, I think Luis has asked it about, but I think the duration of let's say the sample, right? So when you speak, of course, so is there a specific requirement, let's say within this amount of milliseconds, you should be able to detect the emotions, or why, it's cutting, for example, Luis was speaking, but halfway through it cuts off and then, detects
yes,
it.
This is a method for how the offline model is running right now. So basically, you try to have it do these little time slices. So speak for 5 seconds, and then it should process for 2 seconds. And we've added a delay of 15 seconds so that we can think about what the results are. And a real application, you would actually want to have this online. So it would just always be running, and it would always have a constant output at a certain given synchronized timestamp. So this is just a demonstration.
Yeah, that's indeed from the designer's perspective. I was thinking, or at least to see, why you came up with that decision, having those alternative one indeed continues online, and alternative 2 is indeed having such specific samples, and then compare, so I would like to see, or maybe in your documentation, you already have the rationale behind that design decision.
And to add to that answer, this pause for 15 seconds was done so that the audience could see what's actually happening. We can configure this to have a pause of 1 second or no pause when we run the script. But it's still, as Chris said, it is a blocking operation. So we want to have a real-time streaming, and all the time we can see the results. But for debugging purposes or for demonstration purposes, we put a blocking time operation there so that we can actually see what's happening.
Okay, so that clarifies things, but yeah, it's good to clarify because I thought it was a major design decision or maybe specific requirement from the client to to record it. Okay, that clarifies it. The another one is okay, reliability, duration. Yeah, okay, I think it's precision, but I think Chris has answered the questions. Okay.
Yeah, actually, I think it's a nice comments. I want to add also this delay eventually, as you were commenting, is important if you explain at the end why you specify 5 or 2 seconds, because it might have an impact also on the accuracy of the model. Because, for example, one way you can for both cases, something you could do is averaging the average of over, let's say, 10 seconds, and then then after those 10 seconds decide which is the emotion that is more present, because maybe 1 frame is not enough, or one second of audio is not enough to give you a good estimation, and you need more in order to give a reliable output. So as you were commenting, it's important to put the rationality behind, because maybe you want to try with different windows here and see which is the one that performs better. So, yeah.
Yeah, what also might be a nice idea is if we use the text-based model, so to say, because it detects when a sentence is actually over. and use that period of time to actually cut off our detection of a sentence, such that we always have a full sentence, and then we can repeat that.
Yeah. Okay. So yeah,
Something
I think
like that.
yeah, could be. But as you were pointing out, it's important to put it in the rationale behind why the specific design. And also, I just wanted to mention that it was it's quite interesting to say that at this moment the data set is quite generic, and in the future work it could be to get data specific for each. Let's say we know the astronaut for each astronaut, so it can be trained ad hoc for each of the astronauts. And another possibility for future work, I don't think is going to be in the scope of this project, but it's, maybe we can mention, is online training, which is something the model can still be training online during the deployment. So now we are doing all this offline training, but it could be also nice. But I don't think it will. We will, unfortunately, I don't think we will have time in this 2 months project. Maybe another one.
Yeah, we won't. I'm sure we won't have time for online training or type of reinforcement learning or transfer learning. But we have kept it in mind in our design decisions. So in the future, it's definitely possible for you to hand this off.
For transfer learning, actually, you might actually have time for that, because maybe you want to use transfer learning if you're going to apply transformers or one of the recurrent networks. You might want to use transfer learning already there, so that can be done offline as well.
Yeah, that's true.
So maybe for that, yes, but yeah. Okay, thanks.
All right,
Okay.
great. Are there still
Luis,
any questions?
Oh yeah, I have
sorry,
one last question, Luis. Do you, of course, besides the public, let's say, speeches or talks from the astronauts from ISS, do you have also internally data of the astronauts? You know.
No,
It's
unfortunately, that would be really nice. We might, but at this moment we don't have more internal data for this. But we are, as we commented when we proposed the activity, we are trying to kick off several related activities around this idea. So maybe in the future we will get more data. But at this moment, unfortunately, we don't.
Okay, thank you. Okay. Nice.
Great. Are there any questions left from anyone? If not, then I would like to wrap up this midterm presentation. Thank you, everyone, for all the useful comments and all the questions. And we're really excited to continue this project in the upcoming weeks. Thank you.
Okay. Thanks,
everyone.
everyone.
Thank you very much.
See you next week again.
Yep.
Wonderful.
Thank you.
Bye, guys. Thank you.
Bye.
Ciao.
Bye-bye.
Ciao, ciao.
Bye.
Thank you.
Goodbye.
Bye.
Bye.
Bye.